There are two different ways to name alcohols. One uses what we call the common names, and the other uses the systematic rules to name compounds, the IUPAC systematic nomenclature. Let's first take a quick look at the common names, and then we'll get some practice using the nomenclature rules. The one-carbon alcohol is called methyl alcohol. If it has two carbons, it's called ethyl alcohol. By the time you get to 4 carbons, you can have more than one skeleton, and so we need to have a little bit fancier name. Rather than calling it butyl alcohol, we have to say what the carbon skeleton is. So this is isobutyl alcohol because it has this 3-carbon chain and then 1 carbon branching from it. There are a couple of ringers that have common names that you might want to be familiar with. One is ethylene glycol. It doesn't contain a double bond, but we call it ethylene glycol because it's made from ethylene. And glycols are diols. So this is a 2-carbon diol. And this is the alcohol that's used in antifreeze. And propylene glycol would be the one that's made from propylene, and it too is used in antifreeze. So the common names you see here give you some idea of what the alcohol is. Other common names give you no clue what the structure is. You simply have to memorize it. Here's an example. This is a compound you probably have smelled. It's used widely in fragrances. This one word, geraniol, tells you everything about the structure. You just have to memorize it. It talks about the stereochemistry, it talks about where the alcohol is, the branching for the methyl groups, the whole thing. Geraniol is this exact structure. But again, if you don't know the structure for geraniol, you'll have to look it up because this common name doesn't tell you anything about the structure. That's why the systematic rules were developed, so that you could look at the name for any compound and write its structure solely based on the name that you're seeing there. You can see the arrangement of all atoms, the stereochemistry, the whole business. Let's review the rules, and then we'll look at a few examples. The very first thing you do is identify the highest priority functional group. Once you've identified that functional group, you find the longest chain that contains that highest priority functional group. It may not be the longest chain in the molecule. You write the alkane name of that longest chain. You change the ending to reflect the functional groups that are in the molecule, and the highest priority functional group is placed last. Then you'll name substituents, putting them in alphabetical order in front of the name that you've just written. You have to say where those substituents are, so you number the chain, beginning from the end that's closest to the highest priority functional group. You'll use the numbers for the substituents in the name, placing a number in front of each substituent to show exactly where it is in the molecule. And then finally, you'll add way out in front of everything else any needed stereochemical designators like R or S or E or Z. This set of rules will let you name any compound that you see. Take a look at this structure. The hydroxyl group is the highest priority functional group. So we'll locate the longest chain that contains that hydroxyl group. We can find a 7-carbon chain. So this compound is a heptane, only we changed the name of heptane to heptanol to tell us there's an alcohol there. We'll find the substituents attached to this chain, the chloro group and an ethyl group, and we'll put them out in front of heptanol in alphabetical order. Now we need to use numbers to tell us where everything is. So let's number the chain beginning with the carbon at the end that's closest to the hydroxyl group. So this is 3-heptanol. There's an ethyl group on the 4-carbon, and the chloro group is on carbon 7. We're close to done with the name, but we still have to designate the stereochemistry at that stereogenic center. Using the Kohn-Ingold-Prelog rules, we'll assign a priority to each of the 4 things that's attached to this stereogenic center. Hydroxyl would be 1. The hydrogen is obviously 4. This carbon with substituents on it is higher than this carbon, that is a CH2. Now we ignore number 4 and we go in a circle from 1 to 2 to 3, and because we're going in a clockwise direction, we'll call this the R stereochemistry. And there you have it. a name that lets everybody draw exactly the same structure. Let's take a look at another example. There are two functional groups, the hydroxyl group and the carbon-carbon double bond. So this is an alkene in an alcohol. The OH is the higher priority functional group. We need to find the longest chain that contains the functional groups. So here's our chain. It's 5 carbons long, and this is a pentene-all. Remember, the higher priority functional group goes at the very end. Now we'll identify substituent. This is the N-propyl group. To number the chain so we can say where everything is, we'll begin with the N that's closest to the functional groups. And then we'll insert numbers that tell us where everything is. The hydroxyl group is on carbon 3. The alkene, the double bond, is on the first and second carbon, so we call that 1. And the N-propyl group is on carbon 2. So here we have it. We have 2 N-propyl, 1 pentene 3-ol. And we'll use parentheses for the N-propyl group just because it has its own dash. Finally, we have a stereochemical designator. Again, there's chirality, so we'll have to assign R or S. Hydroxyl is highest priority, hydrogen is lowest. This carbon with the double bond and other substituent would clearly be the second priority over this CH2, which is third. We go clockwise direction. So again, we call this R. 2 N-propyl, 1 pentene 3-ol. Here's an interesting case. This is obviously the highest priority functional group. It's the only one. There's a 4-carbon chain that contains it, and there's a 5-carbon ring, more carbons. There's a 5-carbon ring attached. How do we deal with that? Well, we're going to call this ring a substituent, and we're going to call this a 4-carbon chain containing the highest priority functional group. So it's butane, and we'll change that butane to butanol. It has a single substituent, the cyclopentyl group, so we put that out in front. Now we'll number the chain from the end that's closest to the functional group and use those numbers to tell us where things are. The hydroxyl group is on the second carbon, so it's 2-butanol. And the cyclopentyl group is on the 3-carbon. Again, there's chirality in the molecule, which we'll need to designate as R or S. Highest priority is oxygen. The lowest priority is hydrogen. We have 2 carbon atoms. This one is more highly substituted. We'll call it the 2, and this is the 3rd priority. We'll go in a circle from 1 to 2 to 3 and find ourselves going counterclockwise. It's the S configuration. So there you have it, S, 3-cyclopentyl, 2-butanol. And finally, let's name a cyclic alcohol. Highest priority functional group. It's on a cyclopentane ring, so we'll call it cyclopentane-ol. We have 2 substituents, 2 methyl groups. Because we have 2 of the same thing, we'll say dimethyl. We'll need to say where the methyl groups are, but we don't say where the alcohol group is. It's always understood to be on the first carbon. So we can move this name, dimethyl, to close the gap. We don't need a number. We do need to number the ring, so we know where the methyl groups are. This would be carbon 1. We'll go around the ring so that the numbering is lowest when we get to the methyl groups. 3,3-dimethyl. And again, we've got stereochemistry, R or S. The oxygen is highest priority, the hydrogen is lowest priority. These 2 carbons are identical, and they have CH2s, so makes them identical. This is a carbon, and this is a carbon, but this has more substitution. So going this way, this substituent will be higher priority. We'll call it 2. And this substituent will be lower priority. We'll call it 3. We'll go from 1 to 2 to 3. And we find ourselves going counterclockwise. We'll call that S. S,3,3-dimethyl cyclopentanol. So you see, using these systematic rules in this exact order each time, we can unequivocally name even fairly complicated structures.